All right, welcome everybody. We are here to talk about executables and everything having to do with ELF, binaries, and all that fun. And I have a special guest today. I'm doing something different that I've not done before. Amos is here to help me out because his series has been an absolute pleasure to read so far, and I can go ahead and show that now. Here is Amos's blog here that you can read this and, of course, support the further development of this series as well. Definitely worth checking out. And so what we have planned for today is to talk about how Rust creates an executable a little bit. And then we're going to poke and prod at it. We might write some C just to look at what a different compiler does to create an executable. And we will get into a debugger, we'll poke around, we'll look at this thing every which way, and hopefully from there you'll get a better understanding of what an executable actually is and how the operating system and these helper programs actually run your executable when you go to run them. Does that sound good to everybody? Sounds good to me, and I'm in charge, haha. All right, cool. So I guess chat, as always, please make sure anytime you have any questions, we want to make this as interactive as possible. If you want us to go down a path that seems interesting to you, don't hesitate to ask to see something or to learn about something. We have a plan, but it's not really a set plan. So we're happy to go down different ways if you want us to. Without further ado then, I think what we're going to actually take a look at first is creating a Rust binary so that we have one. And so I'm just going to head over here and let me go ahead and make this a tiny bit bigger. Hopefully that doesn't screw everything up. And I'm going to do cargo new hello. And we'll go into here. And of course, we can build that binary like this with cargo build. And if you've done any Rust before, then you know that ends up in your debug folder here. So we have our hello executable right here. And we're going to take a look at that executable. And actually, let me go ahead and add the -h flag here so that we can look in human readable terms how big this thing is. And of course, if you are new to Rust and coming from a C background, typically the first thing people do is they build a binary and then they go, oh my gosh, 2.8 megabytes, that is huge. And it is huge. And so today, one of the things that we're going to be doing is working on bringing our binary size down and understanding what is actually happening when we bring our binary size down and understand why the binary size in Rust is so large by default. I think the first thing that you get told to do when you say, why is the binary size so large, is to build it in release mode. So we can go ahead and do that real quick with cargo build -- release. And if we look at it again in this way with inside of our release folder, then you see that it has gotten much smaller and it's now 2.8. Oh wait, it's the same size. So that didn't really help very much. So release has not really changed anything for us. So then what else can we do? And there's a really great source for this online. If we go to Rust executable size, and I think, yeah, it's this one. Really great resource here by John T. Hagen on how to bring down your size, and we're going to go through a bunch of these. So we've already done the first one, which is building it in release mode. We're going to use strip in just a few minutes. We're going to skip that for now. So the first thing that we're going to do is optimize for size. And so inside of our cargo.toml file, we can go ahead and I'll just use Vim today because why not? And we can just go ahead and paste this in. And so what we're saying is when we build in release, we're going to use the Z flag, which optimizes for size instead of for speed. And I can go ahead and do cargo build -- release again. And if it succeeds, then we will do the LSLAH target release hello, like this. And of course, it helped again by doing nothing, apparently. So we're still at 2.8 meg. So that hasn't really done anything right there. But as some homework, you can try and see if the binary changed at all to see if it actually did anything. I imagine it would, but it hasn't really made that big of a difference. The next thing that they suggest to do is to turn on LTO, which is link time optimization. This provides additional information to the linker, the static linker, and that's important today. We're going to be talking about static linkers and dynamic linkers. To the linker, when they're linking object files together to create our end binary, it provides more information to the linker, and the linker can then take that additional information and remove dead code, and oftentimes bring the binary size down quite a bit with that. So if we go back into our cargo.toml file and add LTO equals true, and then come on, where was it? There it is. Run it again. And finally, we've gotten our binary size down quite a bit. We're at 1.1 megs now. So we've done something that actually makes a difference, which is good. But can we do better? The answer is yes. So remove jmalloc is no longer a thing. This was before Rust 132. Jmalloc was the allocator for your Rust program. Now, since 132, by default, the system allocator. So whatever allocator comes with your system is the memory allocator that gets used in your program. And so we don't have to do anything there. That's already done for us, which means if we were actually building with an older version of Rust, our binary would possibly be even bigger than it is right now. So things have actually gotten better. The next thing that we have here is cogen units. And I keep closing my cargo.toml file. See if that makes a difference. Not really. Made it slower to compile, which is a bummer. And it's not really made a difference yet. Let's see. And we have a question from chat. Link time optimization optimize the linking of standard? Yeah, I would believe so, because that's basically all that we're statically linking inside of our binary.
Yeah, I think what's happening is that the standard library is probably shipped as like thin LTO archives, so it is probably eliminating some stuff. Like everything else that Ryan's been trying on our Hello World probably didn't have much impact because it is pre-built. So like we need some amount of code for any of this to make a difference.
Yeah.
We can probably get a larger project for you to compile if you want to show it off. Otherwise, know that these are good advice. Like it just doesn't show much in a Hello World, but yeah.
Exactly. Hello World, there's not a ton of room to work with here, but it is interesting to see, even with Hello World, that we are so large by default and can still eliminate so much code with a couple of easy flags to add to our binary. And we'll keep going. The next one is abort on panic. And I think this is an interesting time perhaps to introduce our first kind of inspection into our binary. The reason for that is if we go ahead and do object dump here, and we pass -d for decompile, and I will go ahead and, out of habit, just do -big M Intel, which changes the assembly output that we're going to get from AT&T to Intel, because me and apparently the rest of the internet thinks that Intel is easier to read syntax-wise. I don't know. I don't know who likes AT&T, but they're apparently out there.
The GCC people.
Yeah, I guess so.
Maybe they're just stuck with it. I don't know.
Yeah, I don't know. It's I find it much more confusing, but that's neither here nor there. And then I think what we can do is -j and give a section, I believe. And you can see all of the code that we have here. So this is the actual executable code, and I've if we go back to what I ran here, I was printing out the text section here, and text section is the section of our binary that holds our actual code. And you can see that there's quite a lot of code here that we have. A lot of code here. And if you actually, I encourage you to do this, poke around in here. Most of this will not make any sense because, what are you supposed to do with this? This is some stack manipulation, maybe, who knows, kind of stuff. But if you look at the symbols that end up creeping up in your binary, which you typically end up seeing is stuff around backtraces. If you keep looking around here, you'll see a lot of stuff on basically on unwinding, on panic handling, stuff like that. So there's a whole bunch of stuff in here that doesn't have to do with it either. But there's just a lot of code in here that ends up having to do with panic handlings, which is exactly where we're getting to now, where we are changing from panic unwind to panic abort. And if you're not familiar with the distinction in Rust, by default, when you hit panic, what happens is, let's say you're deep inside of the call stack somewhere, you've been calling function, you're all the way down. What Rust will do by default is unwind the stack. It will go back up, it will call destructors for everything inside of the functions that you're in, until it finds a panic handler. So in Rust, you can catch panics. It's not how you normally handle errors, but it is possible to do, where on a thread boundary, you can say, I want to stop the panic from happening here, and then you can continue on. Or if you change to panic equals abort, which we have right here, what happens is the process simply stops, it aborts. And in fact, if you look how this is implemented in the standard library, or even in the core library, on most platforms, what happens is the compiler emits a illegal instruction. So it just emits an assembly instruction that makes no sense, and the CPU gets to it and goes, I don't know what that is. What is that? And goes through its normal process that it has when it encounters an illegal instruction, which is to tear down the process and kind of reclaim all of the memory and stuff like that. But if we put this in here, what that means is that we can move to not having to have all of this stack unwinding code. And Chad is asking, is that done using catch unwind to stop the panic from further propagating? And yes, that's correct. That's what's done. And so if we go back into our cargo.toml file real quick, and we do panic equals abort, and we try again, hopefully it's a little bit smaller. Yes, cool. So now we're into the kilobyte territory instead of into the megabyte territory. Well, I guess we're, depending on how you count a megabyte, we might still be in a megabyte territory, but our output here is showing that we have 1,002 kilobytes. So we're down below a megabyte if a megabyte is 1,024 kilobytes.
If I can go back to the chat question for a second. I think the difference is that panic abort is changing the top level panic handler. Whereas catch unwind is something that you use when, you want to run some code, and if that code in that thread does panic, you want to catch it and do something with it. But it's not top level. It's not the same level. But yeah, they do the same thing. Like, they're going to stop the unwinding and be like, oh, this stops here. Here's everything that happened. Here's where it crashed. What do you want to do now?
Yeah, exactly. Cool. So we're at 1,002 kilobytes right now, but perhaps we can do even better. And there's more interesting things that we can do in here that I encourage people to look at. We're not going to go too far today with this, since we're not talking about binary size as the primary thing today. One thing is building your own standard library, where you can choose different optimization choices than are chosen by default. And optimize for size instead of for speed. And another thing is remove panic string formattings, where you can panic immediate abort so that it just really stops instead of having to format strings for showing error messages and stuff like that. And another thing, if you listen to the Ferris Systems people, they talk a lot about this, that core format is very bloaty when it comes to code size. And so getting rid of the use of core format makes a huge difference here. But we will be going using this real quick, which is removing lib standard, because we don't need lib standard to print to standard out, actually. And getting rid of the main function, which Rust does for us a little bit of niceties around calling main that we're just going to get rid of, and expose a main symbol in our binary that by convention our linker knows to actually call. And we'll look at where main gets called inside of our binary later on in the stream. But we can more or less just copy this code right here and change our source file. It's not, oh man, come on, Vim. Oh. What is going on? I don't know what's going on. Don't make me do this. You can see that I've not used Vim on this machine, and I don't have it set up to, oh, yeah. The good thing is we can do, oh, come on. Well, anyway, you can see what it's formatted as right here. We'll clean this up as we go. So real quick, what's happening here is we're exposing our main symbol instead of using Rust's main, which actually doesn't end up being main in the end of the day. And we're using libc's printf, which if you've done C programming before, you should be familiar with. We're going to print hello world to our screen using this printf function, which comes from libc. And libc, if you're not familiar with, is C's standard library. And today, if you have ever heard the claim that C doesn't have a runtime, hopefully today will dissuade you of that myth, that C and of course Rust both have runtimes. They don't need to have runtimes, but on Linux or on any major operating system, they come with a runtime that helps them get bootstrapped up and running. And we'll be looking at that today. libc is kind of a library for hooking into that runtime.
There's a question in chat. Yes, this code will work on Windows and macOS.
Yeah. And in fact, it will work on any platform as long as you have libc with on that platform. Cool. So one thing we did change though is here they have extern crate libc. That's not stable to be able to use the kind of built-in version of libc. So you have to go into your cargo.toml file and get libc from crates.io. And really this is just this isn't really code that we're bringing down here. It's simply just kind of bindings to libc, because we're going to be dynamically binding to libc. We're not bringing that code into our binary. So this isn't really code per se. It's just kind of bindings to that code that Rust understands. And can we do cargo format now? Yes, cool. So now this should be totally fine to look at here. Let us know if you have any questions about that. And if we go ahead and do our cargo build release and see what it looks like here, hopefully it works. And we end up getting very interesting linker errors that we have here. So this is our first look at a linker error, which if you've not used non-Rust dependencies before, you probably have not run into this. Because Rust, way more than C and C++, hides the linking step from you. In C and C++, you compile the code, you get object files from that compilation, which are basically every file leads to an object file. So every C file in a project you have will have an object file for it. And then the linker takes those object files, which are just basically bags of code and data, and puts them together into a form that makes sense for what you're creating, whether that's an executable or a static library or a dynamic library or whatever. And so here we've run into an issue where we have some interesting things going on. It's saying, for instance, that we are referencing libc csu fini and underscore libc csu init. So we have a bunch of symbols that the linker is trying to make sense of, but it doesn't know where these things are coming from. It doesn't know actually like where to find any of these things. Now, Amos, I don't know. I know how to fix this error, but I'm not exactly sure. I haven't dove into why exactly it's happening. Do you happen to know what is going on here?
I've definitely seen that one before, and I think there were two ways to fix it, an old way and a new way. Why is it happening is probably because in non-STD mode, so in regular STD mode, it would link against like those internal symbols. And now you have to use, I think, compatibility crate or something.
I know that one way to fix it is to, by default, libc actually depends on the standard library. And so you can come in here, though, and say default features equals false, and it turns off that dependency, and that makes it work. But I don't know exactly what the feature is turning on that causes these symbols to, because I don't think actually our end binary will have these symbols in it. So something inside of that feature is like causing libc to want to use these symbols, which don't exist because we don't have a standard library that we're linking to.
Yep.
So this should work, hopefully. And it does. Cool. And now, sorry, go ahead.
Nice.
Yeah.
Interesting.
Yeah. We're down to 17K, which is really cool. And we're gonna do one last thing, and this will be the end of the section on making our binary small for today, and then we can start really poking at it. And the last thing that we're going to be doing is stripping symbols, or stripping string data that we don't actually need inside of our binary. So inside of our binary, as we'll see in a few minutes, there's a whole bunch of text, actual ASCII text symbols that are embedded in there. And for things that are statically linked, where we have the linker has already said, this object file has this symbol, this other object file needs that symbol, I'm just going to stick them together, and now they know, now we know how to go from one object file to another, basically. Like if that one object file calls a symbol, calls a function that's defined in another object file, it knows how to get there because we've put the two pieces together, kind of like Legos or something like that. But for this static linking, this all happens statically with a static linker. And once that's done, we don't really need that information anymore, per se. It can help for things like debugging and stuff like that, but to actually run the binary, we don't need those things. And so we can use a tool called strip to actually remove all of these things that we don't need. And still, strip is smart enough to leave the symbols that we do need, the ones that are dynamically needed, that we don't know how to get to until runtime, because the binary needs to know that in order to figure out how to call these or access these things that are only available to it at runtime. And so we can do strip all here, and go in here and strip our binary. And then if we do one last LSLAH here, then we get around 14K. So we're at 14 kilobytes, and that's the best that we're going to be doing today. You can definitely get it smaller because there is more information inside of the binary that you don't actually need to run it. But that involves a little bit more tinkering and a little bit more specialized tooling and stuff like that, which we won't get into. And I think there are a few articles online that are like, what is the smallest possible hello world Rust binary out there? And you can get it to like maybe a few hundred bytes or something like that. You don't really need much more than that.
Yep.
Cool. Were there any questions or anything like that we should mention on camera?
Something about MSVC and C89 in chat.
Yeah, it looks like. Here's an interesting. So is Rust standard just a wrapper around libc? Yes and no. So in many ways, yes. In many ways, you can think of the standard library as wrapping libc, because at the end of the day, a lot of stuff that happens inside of the standard library will ultimately go through libc. So when you open up a file, for instance, and of course, this really depends on the library or the platform that you're on. So you can be on a platform that has a standard library where they have not used libc as a dependency of that standard library. But for Linux, your standard library oftentimes will ultimately call libc to do things like open a file, map memory, things like that. Because Linux as an operating system generally exposes itself to the world through libc. And so you don't need libc, but at the end of the day, Linux really has made the decision that its primary programming interface, or its primary API to user land applications is libc.
Right. So, like, I know what Chad is thinking. Brian, that's not true. What about system calls? And the answer is yes, but libc is still the best way to do system calls, probably. Yeah. Like you can do them without that. I think Go does them without that. You can read my Reading 5 the Hard Way series, talks about that. But yeah, you want libc. Also, when you start going into stuff like thread local storage and everything, you have to interact with pthreads. And pthreads and libc kind of live in the same monorepo. They're like very tightly coupled. So yeah, you want libc. But there's also a whole lot of Rust-only code in std, like all the collections and everything. So like as you said, it uses it to like handle files and network sockets and memory mapping and whatnot. But there's also a lot of just Rust code.
Yeah. So that's why we came down to the answer of yes and no. It should be noted that you don't need standard, as we've seen here. So therefore, you don't need libc. And if we're still depending on libc for our printf function, but you can go as far as to and I believe this is only possible in Nightly, unfortunately, but you can define your own _start symbol, which we're going to look at in just a second, which is the real entry point to your program, sort of. And there you can do whatever you want, and you don't actually have to call into any libc function whatsoever. And you can be completely free of a libc dependency even on Linux. Which is totally fine. Then Chad is also asking, doesn't Cargo have strip built in now? On Nightly, I think it does, but not on standard. I'm pretty sure that there is now on Nightly a option to strip binaries by default, but I don't believe it's that it is stable yet.
Yeah, you can add strip equals symbols in the Cargo toml file, but that's Nightly only.
Cool.
Yep.
Yes. All right. Real quick, somewhat off-topic question here about Rust progress in the past year. What's the biggest thing that's happened in the past year? if async await was in the past year, which I believe it was, then yeah, that was the biggest thing. But we're not talking about async await at all today. So,
Oh no.
I definitely recommend looking at the releases. Markdown file on the Rust GitHub page. There, they have basically for every release the big things that have happened in that release. It's very accessible, very easy to read. You can catch up pretty quickly there. So check that out for sure. And what the question on safe transmute, we'll talk about if we have time. I can talk about that at the end, but remind me at the end if you still have that question. I am also excited about safe transmute. That's cool. So now I think the thing that we should do is talk about how binaries get run, at least at a high level. So everybody is familiar, if you've written Rust before, with a main function, and if you've written C before, you also have a main function. But the reality of the situation is that the first thing that gets called in your binary isn't main. There's a whole bunch of code that the compiler and the linker have added to your binary on your behalf that gets called beforehand, and perhaps we want to inspect that a little bit. And that will quickly get us down deep into rabbit hole stuff that we can go into. Does that make sense? Should we do that?
Yeah.
Okay, cool. Then I guess the first thing to talk about is what a binary file actually is real quick, so that we can, when we're inspecting it, we know what are we actually looking at. So I think an interesting thing to do is to use this file utility on Linux, where when you run file, it will inspect the file and give you its best guess on what it believes the file to actually be, which can be wrong, but for our executable file, it gets it very right. And so we can see what our executable file actually is. Our executable file is an ELF file, 64-bit, which makes sense. Shared object file, we'll talk about that. We don't need to talk about the version here or system V stuff, ABI. Dynamically linked, we're going to be talking about that. And this is also an important one that we'll be talking about today, this interpreter, which I think MOC will probably take over then to really dive into that if you feel comfortable with that. So at the end of the day, on Linux, our executable file is an ELF file, which ELF stands for executable and linkable format, or I believe, or file. I'm not sure which one.
Something like that.
Yeah.
I keep forgetting what it actually means.
Yeah. And it is very much supposed to be a pun with elf, as in elves, and then that's where you get dwarf files and stuff like that. But elf, just like everything else on Linux, is just another file, and so it's actually very easy to take a look at it, to understand it, and there are a bunch of utilities to poke at the file. And I think we've already seen object dump, which we will take advantage of today, but the other major one I think that we'll really be using a lot is readelf, which we have here. And readelf, as the name would indicate, allows you to read an ELF file and make sense of it. And the first thing to do with a readelf file is to take a look at its header file. So if we take a look here, we can learn some things that actually the file command already told us about it, because it's mostly looking at the header file itself. And so you have like magic up here, and if you decode this as ASCII, it's ELF here. That it's little Indian, it uses system V, ABI, blah, blah, blah. This is an interesting one that we actually, by default, when you create an executable with Rust, you don't actually create a true executable file. You create a file that is executable, but it is not an executable in the purest sense of the word. It is actually a dynamic shared object file that can be executed. and this has to do with position independent code and stuff like that. I don't think we're going to have time to get into there. Very nice. I don't think we're going to have a chance to get into that today. What position independent code is really all about, but something that if people are interested, we can look at another time. And then down here at the end is really the big thing that we're going to be looking at. An ELF file is a collection of sections sections and program headers, are really sections and segments. And what this all, even though you don't really see segments here, what this all really means is that the sections are there really for our static linker to look at to make sense of our executable file or our object files, and our segments, what are designated by these program headers here, are how we move our executable file into memory to actually be executed. And so these program headers collect up sections and say these sections belong together in memory and they should go into this part of memory. Cool.
So you may have noticed Ryan is struggling a bit with the terminology. It's not Ryan, it's just the format, because like program headers are actually segments and then there's sections, and it gets very confusing very quickly. I should know, I wrote like 13 parts on this and I'm like, wait, is this segments or sections?
Yeah.
Which one is this?
Yeah. This is one area where I think Windows is a little bit easier to understand, because there is not a distinction in Windows between segments and sections. Everything is used by both the linker and the static linker and the dynamic linker for mapping things into memory or for manipulating things at link time. But there are advantages to how they've done it here, and there's a flexibility of it. If you look, for instance, at an object file, so when you compile a C file, for instance, and you get out an object file, you'll notice that its program headers are empty. It doesn't actually have program headers because it is not meant to be executed, so it doesn't need to be mapped into memory. Was that enough to say about that? I don't know if I just made everything more confusing, but chat.
I think an easy way to think about ELF files is just to think of them as like a database. So you're going to have, I don't know if that makes it clear or more confusing either, but like it's a database that has different things in it. And some things are like, what is the actual code that we want to run? Some things are like, if we have global variables, what's their value and like how big are they? What's their name and everything. Then you can look up different symbols by their names. It's just a database. You can query it. And there's two kind of different views on it. One for the linker, like find symbols and link together several objects, and one for the dynamic linker or dynamic loader. See, it's confusing. Everything has two names.
Yep.
Linux, just roll with it. Which is just to execute and so to map stuff into memory, which I think we'll get into a little bit later.
Yes. I think another thing that confused me is most things that I read about sections were saying this is for the linker, which is true. Like you need sections for the linker to be able to, when you have different object files, to put them together, to fit them together. But they're also important for the dynamic linker or for actually mapping these things into memory, because the segments are composed of sections at the end of the day.
Yeah, actually, this is something we didn't really say. So we say sections and segments, but most often, like they overlap. They're the same thing. Something is like a section is also a segment. So there's like two different indexes, and they point to the same area of the file. Yeah. It's all confusing.
Yeah.
Like when we try and make a dynamic linker in my series, we try using only segments because that's what the actual dynamic loader would do. But then sometimes we have to use a section because like we're looking at symbols. It's a beautiful mess. Yeah. I'm sure there's a historical reason for all that.
Yeah, it's great. Speaking of which, just another shout out to Amos's series that he has here. I think particularly in the beginning as well, this is probably where you're going to find the most information directly on. Here's, for instance, a good layout of what I believe this is just the header. Yeah, the ELF64 file header. Of course, there's ELF64 and ELF32, depending on if you're on a 64-bit machine or a 32-bit machine. And here you can see in memory how these things are laid out, which is really nice. And I think for me, the best thing was to literally, just like in the series, write a parser for this, where you can parse these things out from the file to really get familiar with the layout of the file itself. So check that out.
This is why the stream is a short version, because in the stream we're only using tools that already know how to parse ELF. But in the series, we actually built those tools, so that's why it's a bit longer.
Exactly. Great. So we know that an ELF file is composed of sections. What do those look like? We can use read ELF here to read the sections. And here's what the sections are about here. And you can notice that it's really the section headers that we're looking at here, not the sections themselves. The section headers are simply just the metadata that describe a section. And then depending on what that section is, the content of the section will vary. Sometimes it's string data, sometimes it's code, sometimes it's whatever. We've already mentioned one section in particular that's very important. That's the .txt section, the .text section, and that is where your code lives. So most of the code that you write, or probably in fact almost all the code that you yourself will write, will end up in the text section here. Yep. Another interesting one is RO data. That's read-only data. So when you write, for instance, a constant or something in your program, it will end up in RO data, and we'll look at that in just a second. What's another good one? You have BSS, which, do you remember what BSS actually stands for?
I don't actually. Yeah. I know it's confusing. It's like block stop something.
Yeah. So BSS is typically not a section that actually contains any data, because it's meant for data that's zeroed out to begin with. So if you have some data that you will start with at 0 and then fill up at runtime, the BSS section says, hey, I need like this much data to be zeroed out. And that's for the interpreter to know how much to map out in memory for zeroed out data.
Okay, so BSS actually stands for block start by symbol, and that name comes from the mid-50s.
So yeah, we're dealing with some very old stuff today. So we're going to be looking at a bunch of these things today. I hesitate to talk much more about them without diving into what they actually are in detail, because if we talk about what they are without looking at them in detail, it won't make any sense what they are. But hopefully those three ones make sense on their own. Let us go ahead real quick and take a look at the text section in detail. And we can use object dump to read that section and to disassemble it so that we can look at the actual assembly code that we have. I think if we do real quick read elf -x and then .txt, then this will give us the section just as hexadecimal code. So this is the raw binary view of that section. So this right here is basically all executable code. But of course, when you're looking at it as a bunch of not ones and zeros, but hexadecimal stuff, doesn't really make any sense. So that's why we can use object dump instead to read the text file instead and actually disassemble it. And so for that, you use -j to get to a particular section, -d for disassemble, and then -m, of course, to get Intel syntax instead of AT&T, because we don't want AT&T syntax. And here, we've already run this before, where we saw a ton and ton of code that Rust-C was producing. And now that's a whole heck of a lot less code that we have here. So this is our entire text section here. and it's much, much shorter. Now we've stripped symbols, which makes this a lot harder to read than it would have been otherwise. So I'm going to go ahead and rebuild so that we have those symbols again. This will make our executable a little bit larger. We'll go from 14 to 17 kilobytes, for instance. But those 3 kilobytes, yeah, are very helpful when we're looking at this code. So cargo release, cargo build, release, and oh, interesting. What is going on there? Not sure.
Good question.
Not sure what that's about. It seems like right where our symbols are supposed to be, there's some warning. Any idea what that might be?
I would just go at it with like GDB, which is better at disassembling. Upstamp is pretty primitive.
Yeah, that's true. Do you want to, since my GDB skills are so terrible, do you want to try and take a look at the code through GDB?
You can try, sure. Let's see. Oh, you want the release build, right?
I don't think we have a debug build.
Okay.
We can create one if you want to, but then, of course, it will be much larger.
So do we have main? We don't even have main. Yeah, it's definitely no symbols here. I think it maybe didn't rebuild it. Like maybe
should we clean? First. Yeah.
Yeah, there you go. And then still nothing. Maybe in debug. Ah, no.
Yeah, we can't build in debug because we have no no standard, but we also have panic is unwind on it. We can change debug to panic abort, and I think that will fix it. Should we do that?
Yeah, go ahead and try it.
Yeah, we can try that. Let's see. So
we're all learning about new things today.
Yeah. Of course, all these options that we mentioned before were only on the release profile. So if we want to also have some of them on our debug profile, then we need to add them, and we can just use panic equals abort for now. And we can do LTO equals true. That shouldn't have too much of it. Oh, did I call it? I think it's not debug. It's, what is it?
Development?
Dev.
Is this dev, maybe?
I think, yeah. Yeah, there we go. Okay. Want to give it a try now in GDB?
Sure. Still no, what? Oh, no, I'm still doing release. That's my bad. Okay, we got symbols now, so if we disassemble main.
So now you can see why having symbols in your binary is actually quite helpful, and why they're usually there is because of this exact reason.
I mean, we could have analyzed the executable, even the release one, without any symbols, but it would not have been as easy from GDB at least.
Yeah.
And now we got cool colors. Look at this.
Yay. Cool. So this is our main function that we have here, and again, more or less the main function that we wrote, because in our Rust program we exposed a main symbol. So normally what Rust does when you create just the normal Rust main function, symbols in Rust are mangled, meaning their names are not what you call them, but the compiler adds a bunch of metadata to them. But we, the linker expects an actual function called main with MAIN as the name of it. And so that's why in our code, you'll notice that the main function that we have there, we put no mangle on top. And that tells the compiler, don't change this name to 34 underscore main at or whatever, but rather call it main, MAIN, and expose that symbol to the linker here. And there you go. You can see up here the no mangle right here. All right. Should we take a look at what calls main, or rather, what calls the thing that calls main? The underscore start
Sure.
symbol.
Definitely. I don't know how you want to do. Is this full demo time, or do you want to go back and forth?
You know what? Take over. Like you can go ahead, and everything I've said so far has just been a suggestion. So you go and show people interesting things.
Okay, so far we've started GDB and we've loaded the file. We can also do that in 2 steps. Just start GDB and then use the files command, and we get tab completion, and then we get our thing. So it's just reading symbols now. This is not gonna be a full GDB course or anything. But what I can do is I can set a breakpoint to main. It even tells us in which file it is. That's also part of the debug symbols that you throw away when you strip a binary. And then I can just run it. And then we can see that it actually broke at main, but it's saying 9 here. Oh, that's the line number. Actually, yeah, the backtrace is 0. So the question is, did it actually start at main, or did something else happen beforehand? Is everything fine with the stream, by the way? I've been getting weird delays from my end. Chat, say something if something's wrong. Raise your hand. So yeah, ls doesn't work. It's not a GDB command, but backtrace does, and it's like, you know what a backtrace is? It's like when a function calls another function, you put it on the stack, and then you get a stack calls. We were talking about unwinding. It's like going down the stack, but when you call a function, it builds up the stack. And so the question is, did we actually start at main, or did we not? And the answer is no. Sorry to spoil it for you. The answer is, if we do start I, it's going to break on the very first thing that it knows how to break, and we're going to end up somewhere else. The stream is still weirdly delayed for me. I'm going to try and open it another tab. Sorry about that.
Is the terminal delayed, or?
No, it's fine now. Everything's fine.
Okay.
Okay, so as you can see, now the stack trace, like when we first started the program, the stack trace looks a tiny bit strange. There's no main. Also, you can't see me selecting stuff because it's only remote terminals, but you can see that the bottommost stack frame is just null, it's just 0. And then there's something else, and then we got 1, and then we got something else. So clearly something's happening there, and that's not main, it's before main. And that's the, Ryan was talking about the static linker earlier on, which is the one that happens after the Rust compiler and LLVM are done generating a bunch of object files. You get the static linker that comes in and takes all those object files and then make a binary or a shared library or everything. This is the dynamic linker, also called the dynamic loader. And this one, actually, remember how I said that ELF files are kind of databases? This is the program that reads that database and then does something with it. So if we do keep going, I can break main still and then continue. We're going to eventually end up at main, and then if we do backtrace again, you'll see that now we only have one frame, and it's main, and everything is fine. And we got like our first parameter is argc, so we got argument count, and then we got argc, which is a pointer, and then everything's fine. So something happened in between those 2 points. And if you're curious, we can step through it, but it's not going to be pretty. Here's everything that happens. Don't blink. You might miss it.
Yeah.
So we could keep going like that for a while, but I guess I'll just summarize what's happening if that's what you want, Ryan.
Yeah, real quick, just a couple of questions.
Sure.
First, there was a question about why there is a question mark right here.
Oh yeah, let me get back to that point. Here, okay. Question mark is GDB saying, I don't know what that is. I don't know what that address is. This GDB doesn't know about like address 0000, which I call null, but null can technically be anything. There's no symbol that is associated with that address, so GDB just says, I don't know what that is, but it's on the stack, so clearly we're there. But yeah, but if you go, like if you actually go to main, you can see that it would normally show the function name, symbol information, and everything. So it's just lost basically. GDB is out of its depth. It's like, no, this is before main. I don't know how that works.
And another thing, just to maybe we can take a step back to talk about when I'm on the command line and I run, ./my executable or whatever, on a rough, like going all the way up to where we hit main. What at a very high level, because we've not talked a lot about some of the concepts that happen there, but at a very high level, what happens to get us to the main function?
So I might get some of this wrong, but that's why there's two of us. I think the first thing that happens is actually a system call. Like so in the shell is a program like anything else. This is bash, I think. Probably bash. Yeah. And then when we run target debug hello, what happens is that, I don't know, bash probably does some text processing and eventually calls exec and says, hey, this file called target debug hello, I want to run it, right? And then the kernel, am I completely wrong? Is exec not a syscall? I'm having doubts about this part.
It's a syscall, yeah.
It's the only part I didn't cover, right? So and then the kernel is like, okay, so you want to execute this, and then the kernel looks at this, and depending on what's inside, for example, if we got a file like this, and then we make it executable, and then we try and execute it, it looks at the first few bytes of the files, and then it finds what's called a hash bang. There's a bunch of different names for it, but basically the first 2 bytes are like hash and bang, and then you say, okay, so the kernel says, I don't need to do anything special about this file. I'm just going to execute bash to use bash to execute that file. But if there's none of that, if it starts with what we've seen, which is ELF, as you can see here, the kernel's like, okay, that's ELF. I know how this works, and then the next thing that's going to happen is it's going to look, does this executable file need an interpreter, or is it statically linked? Ryan, can you think of any statically linked files?
The interpreter itself is statically linked.
The interpreter itself, but yes, any other. Trying to think of any other one.
Not that I can think of. And by statically linked, just so everybody's aware of what we mean here, basically what we mean when we say statically linked is that it has no runtime dependencies. The executable itself is completely self-sufficient, right?
Yeah. So yeah, this one still links against libc. We could do a C one. It wouldn't do much. We could do assembly. What could we do? Do you have NASM? No, we don't have NASM. I don't want to get okay, so an executable like this one that we got here actually does need an interpreter. So it's kind of the same thing. You have a script file, you need bash to execute it, and you have an ELF file, which is a binary, but you also need a little help executing it. Because how do we want to approach this? It's like Ryan said, some executables have different dependencies. So for example, if we look at, I don't know, GCC maybe. GCC doesn't need that many things. What's a good candidate for that? Vim. Okay, Vim needs a bunch of things. That's good. So there's obviously Vim is also just an executable. So if we do this, we can see that it's a symbolic link. Thank you, Ubuntu. And then if we do this, we get the other link.
Come on.
Finally, yeah, we got the actual file, and you can see that it's just the same as our hello file that we did with the Rust compiler, and it's it's 64-bit, it's dynamically linked, everything works fine. It's the same file. It's also kind of it's the same size as the first Rust executable we did. That's just a coincidence, but I think it's neat. And anyway, you can see that this one also needs an interpreter because, as we've seen, if we use LDD to list all the libraries that it needs, you can see there's a bunch of them. There's libm, that's for maths, SE Linux is for secure Linux, Canberra, I don't know, ACL for permissions, GPM, I don't know what that does. DL is to load dynamic libraries at runtime. Python, everybody knows about Python, unfortunately. libc, regular expressions, Orbis for audio, Why does Vim need awk-verbis? Your guess is as good as mine, but it's there. It's interesting. So yeah, so when we run it, the kernel knows how to read from like the Vim basic executable and how to put that into memory and how to start executing it. But it's not going to work if you don't do a bit more preparation work, right? You have to also load those libraries, and the kernel doesn't actually do that. I'm probably going to stop here and let Ryan check that I'm not going too fast or missing anything.
Yeah. So just to repeat, like the kernel loads our executable into memory, but it doesn't really map anything anywhere. And all it really does is check for does this thing need an interpreter? If it does, and the interpreter is this dynamic. It has so many names: interpreter, dynamic linker, dynamic loader. If it has that, it basically hands off to the interpreter this userland program. It's just a totally normal program. The only special thing about it is that it itself is statically linked. It has no runtime dependencies other than the kernel, basically. And it loads in our executable and maps the different sections of the executable into different places in memory. And also, just like LDD, this utility function here does, it looks at our executable and tries to figure out all the runtime dependencies that it has. So for Vim, these 15 things here, and it loads those into memory as well. Can we look at LDD for our executable again?
Sure. Let's do that. So I think there's one thing I disagree about what you just said. You said that the kernel doesn't actually map it into memory. That's true if you need the dynamic loader. But otherwise, they both kind of do the same job. It's just that the kernel's loader is much more simple. It only supports static linking, doesn't know how to load dependency and everything, but it has to understand how ELF files work because the kernel also is an ELF file as far as I know. I think it's in a weird format, but it's still code, it still has to load and run, map somewhere. So if it's a statically linked executable, the kernel takes care of everything, and if it's not, instead of running a program, it's going to run the dynamic loader. And then I guess the next question is, okay, but what is the dynamic loader? Is it a library? Is it magic? How does it work, right? Is that a good time for this question,
yes,
Ryan, do you think?
I think so.
Okay.
I want to know, so.
Okay. So it's the big reveal, isn't it? So if we go to if you use file again, because file is a good command, I like file. See, the interpreter is like lib64, ld linux. So we can use file on that file as well, and it's going to be a symbolic link, obviously, because, Ubuntu. But we're going to keep going until we find a real file, and here we go. It's also an ELF file. That's good. It also says that it's dynamically linked. That's interesting. Let's see if it has any dependencies, and no, it doesn't. So file actually gets this one wrong. I think what it means is that it's position indefinite or something. I don't know. File tries its best, and sometimes it gets things wrong. It's fine. So it is a library, so I guess we could link against it. Let's not even try that because it'd probably be a waste of time. But what we can do is we can run it because it's also an executable. So obviously this is a lot of output, but hang on. Let me just try and make everything fit. There we go. So it even tells us what we did. We've been very naughty and we've invoked ld.so directly, which is not something that you should do, that you would need to do, I should say. It's telling us everything that I'm going to explain, so I'm going to hide that quickly. Point is, we can help the kernel. Like the kernel, when you do this, when you launch the executable, it's going to, where is it? It's going to look at it, see, oh no, it's dynamic. It needs the interpreter. The interpreter is our dynamic loader, which is ld-231.so, which is actually part of libc. See, everything is linked. Linux, just one big ball of. It's not Linux, it's GNU. It's GNU, but and then it actually runs this and passes this. So I'm selecting stuff you can't see it. That's okay. So we can help the kernel and do the first step ourselves. We know it's a dynamic executable, so we can just actually pass it as an argument to the dynamic linker, and it'll run. It'll work. I'm trying to think like if I can show what would happen if it didn't load any of those libraries. I can't think of a quick way to do that.
Can you explain how we know how we know that that's the dynamic? Is it hard coded that that's the dynamic loader that we want to run? What tells us that that's the dynamic loader we want to run?
Okay, so I think Ryan, you mentioned earlier on stream that there are strings in the binary, which makes sense because you can have you can print text. So a global variable could be a string. So there's a command on Linux that's called strings, and we can use it on our binary. And then if we type it to less so that I can page through it, you can see that it's actually the first string in there is the path of the. So it is not hard coded into the kernel or anything. It's in the executable. But what that means is that if you take that binary and you send it to another machine that has a different Linux setup, it might not work. Although that path I think is quite standard now, so it should be okay. But if you put it in a very old Linux system that has different file name, it might not work. We can even look at a hex dump of the whole thing, and I think we should see it somewhere. Yeah, there it is.
It should be its own section, right? There's a section that has the .interp section, I believe is where.
Yeah. We can look at this. What was the command again?
.x, yeah.
No, X, yeah.
Or for read
-x.
For read elf, I think /x should, and then you can give it a section name after it.
Okay. Okay, let's try this. Does it take the dot?
Yeah, it does. Yeah.
Okay, there we go. Yep, you're totally right. It's a whole section.
So that's I guess what is hard coded is to look for that .interp section, to look for the.
Technically, since that's a section, I don't think the kernel even looks at sections. It only looks at segments. So there's probably a segment with a flag that says this is the interpreter. I remember doing that because we actually have to do that in the series. So there's a segment somewhere with a header that tells you to look for that offset and then point to the same data in the file.
Interesting.
So, yeah.
Okay. Yeah, so there's a lot of indirection here going on, right?
Oh, yeah. Big time.
And sometimes it's hard to find the beginning of the indirection where things actually really start.
Right.
I guess we talked about libc a little bit. There is a libc is normally dynamically linked, right? So when we ran LDD on our executable, I guess I have control here. Yeah. libc is one of. So we have the dynamic linker, or the dynamic loader is one of our dependencies. libc is another dependency. I just learned also that Linux VDSO is just a optimization library basically for caching more or less system calls.
Yep.
So
exactly what it is.
So now we know the three dependencies that we have: a system call cacher, libc, and the dynamic loader. There is a way to run to produce Rust or C binaries that do not dynamically depend on libc. And that is by compiling with the target for muzzle, or however you pronounce it, MUSL, as the libc variant. I'm guessing there what happens is we simply don't have a dependency on libc anymore. Do we still have a dependency on the dynamic loader itself, though?
I don't think so. I think you can make it fully static if you want to. That's one of the advantages of maybe you can do a fully static build of glibc as well. Probably much bigger. I don't know. They have strengths, and we can use both.
So what that means, though, is that when you compile with muzzle, which statically, instead of dynamic libc, that's a static libc. Libc is now part of your binary. It's embedded in your binary. That means I can move that binary to another machine, and as long as the kernel is the same and it's the same architecture, right, then it should. And I don't want to say that the kernel has to be the same, but as long as the kernel understands how to run a static file in the same way as our static file is created, everything should just work, right?
Yeah. So I'm actually going rogue and trying to do things while you're explaining this. Sorry about that.
No, it's all good.
I don't know. I only have 15 minutes left, and one of the things we discussed yesterday that I should show is like how do calls work basically.
Oh yes.
Like, how does it work when you call something and it's not in your binary, it's in another library? Do you think now is a good time to
let's
talk
do that.
about
Can we have printf that we're calling inside of libc? Can we show how printf is actually called?
Exactly. So that's what I'm getting at here. I set up GDB. Basically, it's a bunch of like setting up a breakpoint and then stepping until the right moment. And I think this is the moment where everything happens, basically. So there's a lot going on the screen. I'll try to go from top to bottom. At the very top, we got the original Rust code formatted weirdly because shared terminals. But you can recognize like libc : printf. Then the pane below that is just the disassembly. So we've seen some assembly with like obj dump. I don't know if readelf showed that to us. DDB also does that. Also, isn't that AT&T syntax?
That is. It's AT&T, our dreaded AT&T syntax. We don't.
Yeah, we need to fix that. Okay.
We don't allow AT&T syntax in this stream.
Let's start over. Okay, so we run GDB, and then disassembly flavor, Intel, break main, run, switch to this,
Hey.
and then there we go. Wow, that's better. I can read again. So same panes as before. The topmost is the Rust code. Then we got some assembly. Then we got our little GDB command line. And I also started Tmax so that I can have a pane where I can just run some bash commands here. Holding on. I'm seeing a bit of delay on my end.
Yeah, I think it might be dropping out a little bit. Chat, let us know if everything is fine there. If it goes out, we still have the recording.
Yeah. That's true. Okay, so basically, this is actually a very nice. This is the only thing we do in main, but it's a perfect moment to look at the disassembly and like which instruction we're actually executing right now. So this is not. I don't think this is a full assembly course. 12 minutes seems like a bit short for that. But basically, we're moving stuff into registers and then jumping somewhere else in memory. So like registers are basically variables for your CPU, and then you use those to pass parameters to functions. So like here rax is going to be probably the address of our hello string. So this is what rax has right now, and if we inspect this. I need to hang on. There we go. If we inspect this as a string, yeah, you can see that it's a string. So it's moving the string into the REI register because it's going to be the first parameter to printf, and then the other thing, I don't know why it's moving 0xf into ESI. I can't. Maybe it's the variable arguments thing because printf takes a variable number of arguments. Ryan,
I don't know.
Can you see what it does?
No.
Okay. Good. Okay, and then we actually do the call. So let's do this. Let's step one instruction. The console output is getting a bit mangled. That's fine. And then this is not actually a move call. It's just a call. There we go. That fixed it. It's just a call. Okay. It's actually doing a bunch of other stuff. So it's not actually calling printf. It's calling.
Yeah, we're calling as pointer right now. Yeah, there we go.
There we go. Okay, so this is the real one, I think. This is actually going to be printf, isn't it?
And we should mention here this call is an indirect call, right? So it's not calling it's not calling, like, we're not passing the actual location of the function we want to call, but rather a pointer to the location that we want to call.
That's true. So this makes me wonder if it's not the call that I want, because hang on, where are we now? We're in printf.c. Okay. We could just start again.
Yeah.
Let's just step until we get to the printf call. If this doesn't work, I'll just make a small Rust executable. I think it's okay. It's just complaining that it doesn't know how to disassemble that.
Yeah.
Okay. Let me think about how I want to do this. I want to set a breakpoint, probably. Yeah, there's stuff happening. There's stuff happening all over, Ryan. What should I do?
Do we want to create a C file instead so that we don't have to worry about the... So this is the problem with a debug build of Rust in particular. You need debug to have the symbols, but at the same time you're going to be ending up having more artifacts in it because it hasn't boiled away all the high level code that you've written in Rust. So going to C sometimes can be easier because in C you don't have that high level code that needs to be boiled away. You just have the relatively low level C code.
Okay, here we are. Now we don't have the source, which is actually maybe a good thing. We'll just show the registers instead. That's fine. I like registers, and we're actually calling puts, which is interesting. Okay, so what happens here is interesting. I'm going to switch to another tab, I think. But first, I'm going to take note of the process ID of our... in the time that Ryan was explaining that going with a C program to show this is simpler, I was actually made the C program and started debugging it. Sorry if you missed that. I'm on the clock. So... So yeah, I took note of the PID, and what we're going to do with that is we're going to look at the memory mappings. We mentioned memory mapping before. What does it mean? It means so we got this ONOC file, and it's on the disk somewhere, and then we actually want it in memory because we're going to be running it. So we don't want every time that we execute an instruction, we don't want to be doing an I/O request to the disk and then get it back. We want everything laid out nicely in our memory space so that we can treat it as just any other variable, except it's just code. So what we can do on Linux easily, because everything is just text and files and stuff, we can show everything that is mapped into the memory address. And I don't know if we can show this better. Maybe I'll just use Vim. I don't know how to disable wrapping in Vim.
Oh, I forget.
How do I show this in a way that... then disable wrapping. Wrap not. There we go. Okay, so what do we see in there? We see a bunch of address ranges on the left. So start and end addresses, and then we see some permissions. Some stuff is mapped as read, write, or execute, or a combination thereof. And then we see some device numbers. These you can see what those mean in the series. I'm not going to go into details here. And then we can see from which file they're mapped, right? So these at the top are all from our my aptly named C sample, ONOC. And then we got some stuff from libc, and then we got some stuff that isn't mapped from a file. This is the VDS, so this is the system call caching layer that Ryan was talking about. And then we got some stuff from the dynamic loader itself, and then finally we got the stack. So this is like fascinating. We could probably spend 2 hours just talking about memory mapping, couldn't we, Ryan?
Yeah.
Yeah.
Yeah, we could.
But for now, let's just see what's happening here. This is actually going to be more involved than I thought, but I'll try to keep it short. So the address that we're calling, I have this compulsion to type ls in any command that I'm in. Sorry about that. So the address that we got here is just 0x55555505. Why is it 555555? Good question. It's because of GDB. If we weren't in GDB, it would be something else. But GDB helpfully sets up some stuff at 555 and some stuff at 7FFF. So it's consistent between runs of the executable. Otherwise, it would like randomize the place that it's mapped. The address would be completely different, so that you can't guess it, because that would be a security issue. Again, could do a whole stream on just that. Point is, we know the address of this thing, and we can see that it actually comes with the exact address again. So it ends in 5050. So if we go into this other screen, you can see that it's in this mapping, right? Like this one is from 5000 to 6000. And we can see in the permissions here that it's mapped with executable permissions, which is good because we're calling it, so it has to be code, so we have to be able to execute it. So that's good. But it's also interesting because we're calling puts. I don't know if you remember from the 15 seconds that my program C code showed on screen. But we're actually calling printf, but the C compiler is like, printf is too much. It's just a static string. This should call puts instead. Puts is just a function that takes a static string, shows it on the console to the terminal, I guess. And so, but what's interesting is that the function we're calling is not in libc here. It's in our own executable. So let's keep going. Let's keep stepping through the program here, and we can see that it's going to jump somewhere else still. And then finally, I think we're finally in libc now. So what's the address that we're at? 0x7ff. Let's look what this is. FFF, what was it? 7e. Okay, we don't have e. It's somewhere in there, right? It's mapped from libc. It also has executable permissions. So I don't remember exactly what I was going to explain here, but basically you can see that there have been segments from both our executable and from libc that have been mapped into memory at different ranges. And then when they execute, everything is, it's all in the right expected place. And then I guess we're not talking about relocations today, are we, Ryan?
No, and unless you can explain relocations in 3 minutes, which would be very impressive. But I think what to take away from this is that this is the dynamic loader, which took our ELF file, parsed it, looked at the segments that we have. The segments are composed of various sections. Some of that was executable code, and it knew to take that executable code because it was marked as needing to be executable, map it into memory somewhere, mark it as executable so that when we read it, the kernel doesn't complain to us that we're trying to execute memory that should not be executable. And it also does the same thing with our dependencies, namely libc, right? It goes in, finds libc, parses the libc ELF binary as well, reaches in and takes out the code from our libc binary, maps it into a certain place in memory, marks the part of libc that needs to be executable as executable, maps the part of libc that it should be only readable as only readable, and all of our dependencies and our code are sitting in memory in well-defined places based on the description that our database, our ELF file database, has said needs to be in this part of memory. And how we then end up actually executing our puts function, we're going to have to save for another day, I think.
I hope this was helpful. Some people in the chat are saying that GDB is scary. It definitely is. There's lots on the screen right now. I'm sorry I couldn't figure out a simpler way to explain this. There's just lots of moving parts.
I think we should treat this as the first of, if people are interested, the first of a series where we can jump in and look at more things. I think again we've got 1 minute left, but and feel free to ask questions. And Amos, you're free to go in a minute here. The thing.
I've got 5 more minutes.
Five more minutes. Okay, so people feel free to ask questions. The thing to take away from this is we've learned what an ELF file is. It is conceptually a database to describe various parts of how to execute a file, along with dependencies that we can dynamically link to or dynamically reach out and grab and put into memory. They themselves are also ELF files, so they have their own databases that we can dynamically at runtime look into and reach in, grab parts, map them into memory, and give them various permissions depending on if we want to execute the code or not. And that's really what we should take away from this. And I think the thing that we should be doing until the next stream is reading your series to get a better idea of what this ELF file actually looks like, and the various parts that are composed of it. Since you only have 5 minutes left, there's a question for you in chat. Do you have chat open, or I can read it to you?
I do. I'm going to leave you to talk about safe transmute later, maybe.
Yeah, that's fine.
How about the daily life as a programmer? I don't have a job right now, so you go for it.
How does all this theory talk about it? How does it fit into your daily life as a programmer? So the first thing to say is this strictly necessary to be a programmer with a successful career, where you get paid and you can eat and stuff like that? The answer to that is definitely no. You can be a programmer and not know this stuff. Now, should you know this stuff? Absolutely. I think the number one reason for it is it's fun and it's interesting, and this is how your computer is actually working at the end of the day. We're talked about a lot about Linux today, but a lot of this, it works the same way on Windows. The details are different, but at the end of the day, the high level description is basically the same. So we're learning how computers work. And if you know this stuff and things go wrong and your executable is doing weird things, it's so much easier to understand what's going wrong.
Definitely.
When you know where to look and where to poke at to find the answer. So.
And there's a silver lining there, is that if you do learn all this stuff and you finally understand it and like are helpful in debugging it, you're going to be the person they call when they have a problem. So, be warned.
Yeah. So, and there was a question: is ELF better than Mach-O or PE, which are two different executable binary formats on different platforms? Better is a very, very strange thing to ask about an executable format. So I'll say no, they're not better. It's just different. But you can feel free to disagree with me.
I want to keep your stream friendly and everything. They're all terrible, okay?
Yeah.
They're all terrible. They're all the product of decisions that were made in the freaking 70s, and now we have to live with them, and they all have all their quirks. But that's my gut feeling, right? The person I'm writing the series, sure, they're terrible, but let's find exactly how they're terrible and dig into the reasons, and then it's fun that they're terrible. But yeah, they all have issues, and I think they roughly have the same features, right? I can't think of the top of my head of a thing that ELF does that P couldn't or something.
Yeah. I think this is going to be the last question for the day, so that we can wrap it up. We'll do safe transmute next time, I promise. Maybe I can do a whole stream on safe transmute. It's very interesting. So sorry about that. The last question will be on what exactly is the stack and the heap in memory. Is this something the OS provides? Is it CPU provided? Is it something specific to Rust? So the first thing to say there is no, it's not specific to Rust. This is something, the stack versus the heap, and particularly the stack, is something that your operating system knows about, and it's something that even your CPU has special knowledge about, particularly the stack. The heap is really any place in memory that you are allowed to write to. If you're not allowed to write to it, then it's probably not the heap, because the heap is for dynamic memory. It's for memory at runtime that your program needs to use, and you need to be able to write to it and read from it. So if you can't do that, it's not the heap. But other than that, anything in your address space where you can read and write to is basically, that's what you can think of as your heap. I just want to say that the CPU does know about the stack. As far as the RAM itself, or even the memory controller is concerned, they don't know that anything in the RAM is heap or stack. The OS knows, the kernel knows, the CPU knows, but not the RAM itself. They both go on the same physical storage, is what I'm getting at. Yep.
They're just areas on physical storage.
And the stack, the CPU has special knowledge about that, in particular, that there is a stack. There are several registers, depending on which architecture you're talking about, that deal with the stack, like the base pointer, the stack pointer, all having to deal with the stack. Now, what the stack actually is really is sort of like you think of it in Rust or in C. When you call into a function, you have an area of memory that is allocated automatically, basically for your local variables where they live. And when you return from that, that memory is no longer used, and so it is deallocated. Although I think on every machine, I don't think that this is ever the case, that it's never explicitly wiped out. It's just simply no longer used, so that memory is maybe.
I guess it depends. Like you could probably have a build flag that does wipe it out,
Yeah.
or like replace it with garbage just for security reasons.
Yeah.
I don't know.
Maybe.
Also, I want to say that the stack is not something that like we think of it as just something that's there when I write C programs, like for fun. But you can adjust the size of the stack for an executable. You can adjust it probably at runtime. Lots of stuff. They're just conventions, really, and you're right. They're used for like locals and calling functions and everything.
Yeah. Let's leave it there. There's definitely a lot more that we can talk about. To end the stream, first of all, Amos, thank you so much for joining. This was a lot of fun.
Thanks for having me.
Yeah,
It was fun.
I learned a lot. Chat, I hope you learned a lot as well. Please let us know if you want to see another version of the stream, another part in the series. I would definitely be happy to do it. Amos, you don't have to say whether you want to do another one or not live on camera.
I'd be happy to.
Yeah,
happy to.
You're more than welcome to come back. Just to end, where can people find you? Where should they search for you on the internet?
I'm gonna post a link in chat, I guess. It's just if you just search for faster than lime as the fruit, the lemon, you can find me. And that's it. You'll find my Twitter. You'll find my website. There you go. That's the spelling. That's
Nope, not fatter. Faster. There we go.
You can find my music and everything. Lots of stuff. The actual domain is .me. So it's fasterthanlie.me. But if you go on my Twitter, there's everything there.
Great. Then everybody, also please follow me on Twitch, on Twitter, wherever, so you know about the next stream. And we will definitely be doing this again. I want to thank you, chat. Thank you, Amos, and everybody have a good weekend.
Thanks, Chad. Thanks, Ryan.
All right. Bye-bye.